Hi everyone, welcome to episode 12 in our long series of videos for Kinetics. So episode 12 is all about integrated rate laws, and to be perfectly honest, out of the first 3 episodes that we have in this unit, this one is the most important. Reaction rates are great, they're important. Rate laws are super important because you can figure out how concentrations are going to actually affect the overall rate of the reaction, but integrated rate laws are one of the most important things because now you can use concentrations to determine time, you can use concentrations and time to determine a rate constant, so there's a lot of different things that integrated rate laws do. But before I jump right into them, let's kind of review what we already know. So for rate laws, we know that our rate laws, which for example, like the one we discussed in the last episode, where rate is equal to K times the concentration of A raised to the order of X times the concentration of B raised to the order of Y. And so for these rate laws, we can relate the rate of reaction to the concentration of the reactions. So how quickly something is going to occur depends on the rate and the concentration. Those are the 2 factors we need. Now, rate laws tells us the instantaneous reaction rate at those current concentrations. So instantaneous, if you remember from our very first episode, so episode 10, instantaneous rate reactions are at one point on a graph, so one spot. And so when we looked at all of that data, like the table of data, we were looking at instantaneous reaction rates, but specifically at the initial spot, so that initial term. So these would be considered your initial rates. But rate laws can't actually tell us what concentrations will be if we let the reaction run for an hour or 2. So for example, when I was setting up a reaction in lab, I would set it up, put it in my hood, and then I knew that my reaction took a certain amount of time, and so I could plan my day accordingly. This time component helps us as chemists plan our day in lab. It helps us so that we know, like, maybe I could set up this reaction, then I'm going to have 2 hours to set up 4 more reactions, and then come back to this first one. So the time component, the kinetic piece, is really important, but it's often overlooked. So in integrated rate laws, what happens is we can actually show the concentration as a function of time. So we take concentration and time and put them together. Now, this allows us to calculate how much reactant is left after a certain amount of time has passed. So we could say, like, after 30 minutes, how much reactant is going to be there, right? Or how much time is required to use up a certain amount of reactant. To me, the second one is more important. So how long is it going to take to get to 90% completion of reaction? Or maybe you only care about 50% completion, but the time component is huge here. So when working with integrated rate laws, we will monitor only one reactant concentration at a time. This is the big one that I want to draw your attention to. So for reaction rates and rate laws, we could look at as many different concentrations in as reactants as possible. But with integrated rate laws, we can only look at one reactant. And so our generic reactant that we use for this entire unit is going to be A. Okay, so just keep that in the back of your mind. So before we dive really deep into integrated rate laws, we're going to start with a tiny mini activity, which is kind of a review of what we've done in the last 2 episodes. So really quickly here, what I want you to do is pause the video, and I want you to write the rate law for a 0 first and second order reaction in which only reactant A appears in the rate law. Go. Hopefully you're able to come up with the rate laws for 0, first, and second order. So what we're going to do is use that information in the rate laws you just derived to come up with this really big chart that will hopefully help you for the rest of this section, or, well, any of the material in kinetics, really. So let's create our chart. What we're going to do is create a column for 0 order, column for first order, and a column for second order. And then obviously, because I asked you to solve for the rate laws, we're going to start with that. So if something is 0 order, that means that the concentration of that species does not affect the rate at all. So you would say that your rate is going to be equal to your rate constant. Now in theory, you could actually put your concentration of A here and raise it up to 0 power, but we all know that's equal to 1, and so you might as well just not even mess with it. So if something is 0 order, we know it does not affect the overall rate, and so rate is just equal to K. Now, if something is first order, you do have to include it in the rate constant. So you're going to have rate law, rate is going to be equal to your rate constant times A. Again, you're going to raise that to 1, but the 1 is implied, so that's just fine like this. So rate is equal to K times A. So if your concentration increases, then your rate is going to increase just by that exact amount. Now, for something that is second order, you're going to see that that is going to affect the exponent here, and it really affects your math. So the rate is going to be equal to your rate constant times your concentration of A squared. So now here, if you double the concentration of A, you're going to see 2 squared. That's actually going to make the rate increase by a factor of 4. So it really, the concentration really affects the overall rate in something that's second order. Now, what we like to do with this information is plot out our data for our concentration of A versus time, but in 2 different ways. So we're going to do the first one very straightforward, and we're just going to do a natural plot of the concentration of A versus time. Nothing special here. So we're going to do the same axes here, concentration of A. We're going to plot it versus T. If something is 0 order, what we see is we're going to start off with a random concentration, a certain number here at time 0. We're going to slowly use up our A at a very constant rate until we intersect with the x-axis, where we're going to see that we're out of A, we've used it all up, and so it's just going to continue along here where you're equal to 0, right? You're out of your reactant. We can do the same thing for something that is first order. Here we're going to plot our concentration again versus time. And what we're going to see is a really nice exponential decay. So you're going to start up here at the top, it's going to slowly increase, and you'll kind of get something that looks like that. What you're seeing then is as you use up your reactant A, the rate is getting slower and slower because you're running out of that concentration. Again, this is just like what we talked about in the reaction rates in episode 10, so if that's unclear, just go back there. And then we have something for second order. So second order is just going to be a more extreme version of the first order plot. So it goes down just like a lot steeper, and then it starts to narrow out. It's obviously not that extreme, but I'm terrible at drawing with my pen over these recorded videos, so you're going to have to take my word for it, okay? So it kind of looks like that, but less like an L. All right, so now what we can do is then do a little bit of calculus and end up with an integrated rate law. And so our integrated rate law is very specific with 4 different variables. So you have your initial concentration, you have your rate constant, and then you have a time, and then you're going to have a new concentration at that specific time. Now, this doesn't necessarily mean we're talking about your final concentration. It just means we're talking about a specific concentration at time t. Okay? So our integrated rate law for 0 order is very straightforward. It's the easiest one. So you have your concentration of A is equal to your initial concentration minus KT. So you have your rate constant, and then you're going to multiply it by that factor of time. Very straightforward. For your first order one, you're going to use the natural log. So you have natural log of A is equal to your natural log of your initial concentration, and then same thing as before, minus your rate constant, multiply it by the factor of time. Your integrated rate law for something that is second order is a little bit different. So you're noticing this pattern, hopefully. You've got your concentration at whatever time is going to be on your left side of the equal sign, and then on your right side, what you see is your initial concentration, your rate constant, and your time, but it's minus KT. For second order, it's actually plus KT. So you're going to take the inverse of your concentration is going to be equal to your inverse of your concentration initial, and you're going to add that times your rate constant times temperature. And so obviously these are your integrated rate laws. A lot of calculus has been applied to this. If you want to see the math or how these are derived, please come talk to me in office hours over Zoom. I will be happy to kind of walk you through these derivations. Okay, so the last thing we got to do is plot our data. So this thing that I'm about to show you is something that is so crucial and so important if you actually run kinetics and do stuff in lab with using kinetics in these experiments. So what we like to do is take our data and plot it, and we plot our concentration versus time. But we are looking for a straight line plot. So what I would do in my lab or my experiments is I would take my data, and the first thing I would do is see if it was 0 order. That's always what you check first. So you're going to plot your concentration of A versus your time. If you get a line that looks like this, then you're like, woohoo, I nailed it. I've got a straight line. My data must be 0 order, or I must have a 0 order reaction with respect to whatever reactant that I'm studying. And so for this plot, if you get a straight line like this, you would then be able to take your slope, multiply it by -1, and that's going to give you your rate constant. So you plot your data, you get your slope, and that's what gives you your rate constant. Now, let's say you plot your data, concentration versus time, and you get a wonky line. Like it's all wiggly, it's definitely not straight. In that case, what you do is you see if you have any first order data. So here you're going to plot the natural log of A. Okay, look familiar? and you're going to plot that versus time. Again, if you get a straight line plot like this, you are done, you're happy, that's a good sign. That means all of your data is actually first order. So again, what you do is you calculate your slope, multiply it by -1, and that's going to give you your overall rate constant. But worst case scenario, you plotted it here using first order information and you don't get a straight line. So for the second time, you get a wonky line. In that instance, you're like, oh gosh, okay, I have to do it a third time. So for your third plot, what you do is you would do your inverse of your concentration. You're going to plot that versus time. This time, you're hoping for a positive line like this. So if you plot your data and you get an increase like that, where you have a positive slope, and you're plotting your inverse of your concentration versus time, then this is a really good way to indicate that you have data that is second order. So here, unlike 0 in first order, your slope is actually equal to positive k. So all you have to do is find your slope, and now you have your rate constant. I've summarized all this information for you in a table right here, so you can see everything 0 order, first order, and second order. Hopefully you can see all of that on your screen. Your rate law is going to be rate is equal to k. You can see that the concentration, if something is 0 order, the concentration doesn't affect the rate. If it's first order, it's going to have a direct relationship. If it's second order, it's going to have an exponential relationship. And so you can see everything. This is a much better representation than what I tried to draw out there for you, so put that in your brain instead of what I drew. The integrated rate law is, like I said earlier, probably the most important thing that you can take from this lecture. You've got to know these three equations. If you have anything memorized, it has to be those. If you don't know those when the exam comes, you're going to be in a lot of trouble. Okay, and then your integrated rate law plots, or your straight line plots is what we call them in lab. Those are one of the most useful things if you're actually doing kinetics in your lab and running experiments. You're going to take your data, put it into the computer, plot everything out, and from there, immediately, depending on which one of these three gives you a straight line plot, then you can say, oh, okay, I definitely have a first order reaction with respect to reactant A, B, C, whatever it is, okay? All right, so now I've been going on and on and on about why integrated rate laws are wonderful, but here they are written out for you. So here's your first one. Number 1, if you know your initial concentration and you know your rate constant, then you can calculate a new concentration for that reactant at any time t. So 10 minutes later, 20 minutes later, 24 hours later, you can calculate how much of reactant A will be left over at a specific time. That is extremely useful. Number two is the thing that is most important to me personally, because I did this stuff in lab. So if you know your initial concentration and a second concentration at some time t, you can then actually calculate your rate constant k. For me, I had to go through all of my research, all of my experiments, everything just to get the rate constant. If I couldn't calculate my rate constant, then I couldn't publish my results. So the rate constant is crucial in order to validate your data and be able to predict in the future what you could possibly have with these same reactants. And then the last thing, number 3, is kind of what I just referenced right there. If you know your rate constant and A at some time t, you can then back calculate how much A you would have started with. So this is important if you find a sample in your lab that you haven't labeled, or in a general chemistry experiment. But a lot of times this is more a practical reason, just mathematical applications. But 1 and 2 are highly done in lab all the time. Okay, so now I'm going to let you try one. So here's a question for you that I actually want you to do, so please pause the video and do it. So if I give you a gas, N2O, and I tell you that it decomposes under first order kinetics, and I give you your rate law. So your rate law is equal to K times N2O. So from right here, if I had not even told you it was first order kinetics, you would have been able to look right there and notice that they have an exponent of 1. Exponent of 1 means that you have first order kinetics there. So that was your clue number 1. Number 2 is you can actually come over here and look at your rate constant unit right there and see that it is inverse seconds. Inverse time is always going to be a good indication that you have first order kinetics. Because in the future, I'm not going to give you this first sentence. I'm not going to tell you that it's first order kinetics. You're going to actually have to look at either your exponent, your order, or your unit of your rate constant in order to determine that. Okay, now I've told you it's first order, I've given you the rate law and the rate constant. Now my question to you is, if the initial concentration was 0.20 molar, what will the concentration be after 100 milliseconds, okay? Go ahead and try it. Let me clean this up for you so you have a good shot of it when you pause your video right now. If we are trying to solve for the concentration after 100 milliseconds, we need to first figure out which integrated rate law that we need. So we already decided that we have first order kinetics by 3 different clues, including that we told you that. So you need to find your first order integrated rate law in the equation specifically, which is your natural log of A, which is going to be equal to your natural log of your initial concentrations of A, and then minus KT. So then what you have to do is just plug some variables in here. So your initial concentration is this value, 0.2, so we can come over here. Natural log, initial, that's going to be on this side. Natural log is going to be 0.2 molar. Okay, molar. And then you're going to subtract out your rate constant, 3.4 inverse seconds. 3.4 inverse seconds. And our time is given to us 100 milliseconds. Notice that our unit over here is seconds, so that needs to be converted to seconds, which is 0.1 seconds. That's going to be here, 0.1. And then we're going to try to solve for our concentration at that specific time. So if you put it in your calculator properly, you will end up with a concentration equal to 0.14 molar. So think about that for a second. In 0.1 seconds, our concentration of our reactant dropped from 0.2 to 0.14. That's very fast. Very, very, very fast. Like that reaction happened like that, okay? So always put this in the back of your mind, like what these numbers mean and what you're actually solving for. Just don't just solve for things, okay? All right, one more problem. So now what we're going to do is continue to have an initial concentration of 0.2 molar. Okay, that's still the same. But our new question is, how long will it take for the concentration to drop to 1% of its original value? So how long all the way up to 1% of its original value? Try this one. We have first order kinetics, so again we have to use the first order integrated rate law. So we're going to start off by saying our natural log of our concentration of N2O is going to be equal to our natural log of our concentration of N2O original, and then we're going to subtract out KT. So same equation we've been using. And now what we're going to do is just plug in some of our information. So we were told that our initial concentration is 0.2, so that's going to go right here. Natural log is 0.2. We're going to then subtract out our rate constant, which is 3.4 inverse seconds, and then we're going to multiply that by the t, our time, and that's what we're looking for. But we're trying to figure out what the time is going to be when our concentration of our gas is 1% of its original value. So that's going to be 0.002 molar. If you put this into your calculator correctly, you're going to get a time equal to 1.35 seconds, which is so fast. So in less than 2 seconds, this species decomposes like almost completely. How crazy is that? Like that just happens so, just like that, boom, decompose. I think that's so cool. All right, so that's why kinetics is amazing. We can predict how quickly that's going to happen. So this brings me to one last thing we want to talk about before I wrap up the episode, and it's something called pseudo first order kinetics. And so what this is when you have a reaction that has 2 reactants. So that's the first condition. So let's look at our example that we've been having here. So our methyl chloride plus our hydroxide ion. So we have 2 reactants, they come together and they form 2 different products. Now, in our last 2 episodes, we've talked about this rate law. We showed you it in the first one, and then we derived it in the second one. But now what I want to do is put a little twist on it. So instead of having just like normal or relatively equal values of our reactants, now what we're going to do is have one, like hydroxide, that is so high, up at like 2 molar, and then we're going to have our other one, methyl chloride, down here at 0.05 molar. So in instance, what we have is that the concentration of our hydroxide ion is much, much, much bigger than the concentration of our methyl chloride. And when that happens, what we end up doing is basically thinking that our concentration of our hydroxide is essentially constant, meaning it's not going to change relative to the one that we have not very much of. So in this example, what we do is we essentially take the concentration of the one that's super concentrated, so in this example, the hydroxide ion, and we plug that right in and essentially think of it like the rate constant. So in my brain, in a pseudo first order kinetics reaction, the K and the 2 are multiplied together. So it's 2K, and then you multiply it by whatever the concentration is of your reactant, in this case, methyl chloride. Okay, so keep that in mind because that's going to come something that's important later. You'll also see some problems like it on your homework and whatnot, so just make sure you know what that means. Okay. All right, so next time we get to move into really cool stuff. We're talking about half-life. So that's the time at which that your concentration is at 50% of its original value. It doesn't sound like it's something that's very important, but we actually use it a lot in medicinal properties and out in medicine. So doctors and surgeons use it all the time. So if you're pre-med at all, you're going to want to check it out in the next episode. If not, have a great week. Take care of yourself and drink what?